In this video, I'm going to show you how to use the sum and difference identities to evaluate trig functions without using a calculator for angles that we haven't talked about yet. A few units ago, we talked about benchmark angles on the unit circle, 30, 45, 60, and their multiples. But how do we evaluate something like the sine of 15 degrees without a calculator? Well, that's exactly what I'm going to show you how to do in this lesson using the sum and difference identities. So what we're going to do is we're going to take an angle like 15, as we see in example 1, and we're going to express it as the sum or difference of two angles which are benchmark angles. So for example, for this first question, the cosine of 15, we can think of this 15 in a number of different ways. We could think of 15 as 45 minus 30. We could think of the 15 as 60 minus 45. So by looking at this angle here as some combination of other benchmark angles that we already know, we're able to get the exact value without having to use a calculator. So the formulas are over here in the green box, and the first thing that you might notice if you look carefully is that in both the second and third formulas there is a minus plus, and a lot of students think that might be a typo or a mistake, but it's not. There are actually 6 formulas here. There's the sine of a sum, the sine of a difference, the cosine of a sum, the cosine of a difference, the tangent of a sum, and the tangent of a difference. And whatever operation you're using, you have to be consistent with that throughout. For example, if you're deciding to express something as the sine of a sum, you're using the top operation. And if you use the top operation, then you have to use the top operation here. If, for example, you're describing something as the tangent of a difference, then you're going to use this formula, but you're using the bottom operation. And you're going to use the bottom operation throughout. That means you're going to use minus here, but then plus there. So just remember, always stay on the top or always stay on the bottom, no switching allowed. And the A and B, of course, correspond with the angles that you're selecting to describe this sum or difference. So to continue with example 1, find the exact value of the cosine of 15. Now I can use either of these options. I'm going to use 60 minus 45. Okay, so the cosine of 15 is the same thing as the cosine of 60 minus 45. So I'm going to use the second rule, the cosine rule, and I'm expressing this as the cosine of a difference, which means I'm using the bottom operation, and I need to stay on the bottom throughout the entire problem. So it's going to be the cosine of 60 times the cosine of 45 plus the sine of 60 times the sine of 45. What I like to do next is set up little blanks for each of these evaluations. It just helps me maintain a little bit of organization. Now the cosine of 60 from a prior unit I've memorized to be 1/2. The cosine of 45 is root 2 over 2. The sine of 60 is root 3 over 2, and the sine of 45 is root 2 over 2. Multiplying each of these fractions, I get root 2 over 4 for the first product, and for the second product, I get root 6 over 4. Because both of these fractions have the same denominator, I could write this as a single fraction, root 2 plus root 6 all over 4. Now, even though for my students on a quiz on this topic, I would not allow the use of a calculator, while you're learning, I encourage the students to get their calculator out at this time to check to see if they got it right. And I'm going to show you that right here. I've got my calculator ready to go, and I'm going to type in 2 things. The first thing will be the cosine of 15, because that's what the original problem is. And I get this decimal, 0.966. Now I'm going to put this radical in, and let's hope that we get the same thing. And you'll notice I get the same decimal each time, which tells me that I did the problem right. So this is a nice tool to use while you're learning. And then when you get really comfortable, you become more confident that your answer is right and you don't need to check. Okay, let's go to example 2, which is on the upper right. This one is find the exact value of the sine of 13 pi over 12. This one's got a little bit of an added edge to it because the angle is given to you in radians. And I just find that it's much easier if at this time you just switch to degrees. So if you can make that conversion, 13 pi over 12 is the same as 195 degrees. Okay, now you're going to want to think about that unit circle, all the different benchmark angles, and pick two that either add or subtract to 195. And in some cases, there's more than one choice, and it doesn't matter what choice you pick, the answer will be the same in the end. I'm thinking about 135 plus 60. I don't think I stressed this enough the first time in the first example. I just want to make sure you know this guy corresponds with the A in the formula, and this angle corresponds with the B. I just wanted to make that a little bit clearer in case there was any confusion. So now I'm looking at the top formula because this is the formula that involves the sine of a sum, and I'm going to be using the top operations throughout the problem. So this is going to become the sine of 135 times the cosine of 60 plus the sine of 60 times the cosine of 135. And now for organizational purposes, I'll set up little blanks for my answers. I like to do the easy ones first. So I'm going to start with the cosine of 60, which is a half, and I'm going to do the sine of 60, which is root 3 over 2. Now, the sine of 135 places me in the second quadrant, and I know that sine is positive in the second quadrant, and I know that 135 has a reference angle of 45, so this is going to end up being root 2 over 2. When I go to the last evaluation, I know that I'm in the second quadrant, and I know that cosine is negative in the second quadrant. So this is going to end up being negative root 2 over 2. Now multiplying each fraction together, I end up getting root 2 over 4. The second answer is going to be negative because I'm multiplying a positive times a negative. Overall, that's a negative. And now I'm going to have root 6 over 4. Again, I have an instance where I've got a common denominator, so I could write this as a single fraction, root 2 minus root 6 all over 4. Okay, now I'll get the calculator out to check. So I'll start by just entering sine 195 and seeing what the decimal is. Now I'll enter the radical answer, the exact answer. And let's hope when I press enter we get the same thing. And we do. So that tells me I did the problem correctly. Okay, skipping to the last example, example 3. Find the exact value of the tangent of 17 pi over 12. Again, because they're giving me the angle in radians, I just think it's easier to think of combinations when it's in degrees. Just my personal preference. So I'm going to convert 17 pi over 12 to 255 degrees. Now I'm going to think about that unit circle and all the different things that either have a sum or difference of 255. And I'm choosing 210 and 45. Okay, so certainly I'm using the tangent identity. And because I'm using the tangent of a sum, I'm committing to the top operations. Whenever there's a choice, go to the operation on top. So this is going to be the tangent of 210 plus the tangent of 45 all over 1 minus the tangent of 210 times the tangent of 45. Now I'm going to set up all my little blanks so that I can keep some organization in this problem. Doing some of the easy ones first, I know that the tangent of 45 is 1, so I'll go ahead and make that substitution. I know that 210 is in the third quadrant, and that tangent will be positive in the third quadrant, and there's a reference angle of 30, which gives me root 3 over 3. Now, as I'm sure you've probably noticed, we've created a complex fraction here, which is not the easiest to work with, but if I multiply through by a useful form of 1, I could very easily make this not complex. So what I'm going to do is group the whole thing and then multiply by a useful form of 1, which in this case will be 3 over 3. I'll distribute on the top 3 times root 3 over 3, and then 3 times 1. When I do that, I end up getting root 3 plus 3. Doing the same sort of thing on the bottom, distributing the 3 into the 1, and then the 3 into the root 3 over 3, I end up getting 3 minus root 3. Now our answer is no longer complex, but we do have a radical in the denominator. And on an SAT 2, that might not be one of your answer choices. So let's rationalize the denominator so that there's no radical left in the denominator by using the conjugate. So upstairs, I'm going to do a full FOIL, and the first will be 3 root 3. The outer will be 3. The inner will be 9. And the last will be 3 root 3. Now downstairs, I'm multiplying a binomial by its conjugate. And whenever you multiply a binomial by its conjugate, you initially think you need to FOIL, but the outer and the inner will always cancel out, so you really just have to do first and last. I call that Florida, because FL is the abbreviation for Florida. So first will be 3 times 3 or 9. A negative times a positive is a negative, and root 3 times root 3 is 3. Cleaning all this, we have 12 plus 6 root 3 over 6. Now, in my class, if you have many terms over one term, we perform an operation called a mu. Many over 1. Mu. So 12 over 6 is 2, and 6 root 3 over 6 is just root 3. So I'm getting an answer of 2 plus root 3. And of course, we conclude with a check to make sure that we've done that correctly. So I'm going to go ahead and put in the tangent of 255, and we get this decimal. And I'm going to put in 2 plus root 3, and really hope that it's the same decimal. It is. Awesome. We got it right. So let me move this calculator out of the way so we can just do a quick summary. This lesson was on the sum and difference identities for trig, and they're pretty easy. The only complicated thing is this whole, which operation do you use? Just remember, if you're using the top operation in the beginning, stick with that all the way through.